Hello, everyone. I'm Yongwei. Today, I want to show you an ongoing work, pattern matching with type holes. Pattern matching allows us to branch based on a given expression, which is also called scrutiny. We consider branches in order and take the first branch that is matched by the scrutiny. Imagine we have a single element list that begins with 1. First, it's not empty and thus doesn't match the pattern. Then we consider the second branch. The scrutiny begins with 1, so it matches the pattern, and thus we take the second branch. That brings up the question, what would happen when none of the branches will be taken? The answer is that we would either have runtime error or some exception raised, which is not good. Therefore, we want to ensure the coverage of the branches, or in other words, exhaustiveness. The other question is that if we have a branch so that our expression that matches its pattern also matches one of the patterns in its preceding branches, that means the branch can never be reached. Such a branch is actually redundant. There are existing algorithms to check exhaustiveness and redundancy. However, we didn't consider what if the match expression is incomplete. When we are programming for most of the time, we are dealing with incomplete programs. Today's programming language, Haskell, Agda, and Hazel represent the missing parts in the program as wholes. Here we take similar approach. What if we have a hole in the scrutiny? What if we have a hole in a pattern? Can we still consider those branches in order and find a branch for the scrutiny? Or what can we say about the exhaustiveness of the branches and the redundancy of a particular branch? It turns out that we may not be able to fully answer these questions since there are holes in the program. What we can do is to feed our feet in program shows and see what they really want to know about an incomplete match expression. The key point behind the reasoning about incomplete programs is to get feedback that is always correct, no matter how the programmer filled these holes at the end. With that designing philosophy in mind, let's see how pattern matching with type holes works. Even if there are holes in the program, programmers may still want to run the program without sacrificing correctness. There are 2 types of holes in the program. The first one is expression hole. An expression hole doesn't have to stop evaluation, given a list that begins with 1 and is followed by a hole. Since it can be an empty list, the first branch can be taken. Then we consider a second branch. We notice that no matter what we fill in the hole, it always matches the variable access. Therefore, the scrutiny must match the second pattern, and we know that the value of the match expression is a string. The other type of holes is pattern holes. We can still try to match it against the given expression. The given list is not empty, so we consider the second branch. If the programmer filled the hole with 1 or a variable, then the second branch will be taken. Otherwise, it won't be taken. That means at this stage, we can determine whether the second branch will be taken or not. At last, as a result, we regard such a match expression as indeterminate. To conclude, we keep evaluating the expression until we get a value, or if we have no idea how to further evaluate it, it is indeterminate. The other thing that programmers might be interested in is that whether their program is correct, or at least the program may be correct if they fill the holes appropriately. Therefore, we only report errors when they can be avoided. In the next few slides, we will use examples to illustrate when to report errors. Can this match expression be exhaustive? If we fill the holes with some variables, since all lists that are either empty or non-empty, at least one of the branches will be taken. In this case, we shouldn't prompt any error message, since the branches may be exhaustive by filling the hole with a variable. What about this one? No matter what pattern we fill in the hole, branches cannot be exhaustive. And is the third branch redundant in this example? If we fill the hole with number 2 or a variable, the third branch is redundant with respect to the second branch. But we shouldn't prompt the arrow because the hole can be filled with a number other than 2, and the list that begins with 2 can reach the third branch. There are also cases when some branch must be redundant, no matter what pattern we fill in the hole. One, a variable. The first branch has already covered all the cases, and thus the third branch can never be reached. Then the program of the third branch. To summarize, we only prompt the arrow message when the branches mustn't be exhaustive, or some branch must be redundant. Now we want to formalize the pattern matching with type host. For simplicity, we use binary sum type. Here is a match expression in our internal language. One of the main contributions of the work is that other than match and not match, we introduce a third possibility. An expression may match a pattern because by filling the hole appropriately, the expression can match the pattern. We use match constraint language to predict the 3 possibilities of pattern matching. For the emitted constraint, there are also 3 possible relationships between the expression and the constraint, which exactly correspond to the pattern matching result. The constraint emitted from branch is exactly the constraint emitted from its pattern. As for series of branches, we use OR to connect constraints emitted from each branch. If we think of constraints as a set of expressions, then the OR of constraint is analogous to union of sets. To take advantage of constraints to be exhaustive and to do exhaustiveness and redundancy checking, we define entailment between constraints. Entailment between constraints corresponds to the redundancy of a branch with respect to its preceding branches. Now, we can use emitted constraints to enforce redundancy in typing judgment of branches. The one-sided entailment with plus and question mark corresponds to the exhaustiveness of branches. And we can use emitted constraints from all 3 branches to enforce that branches must or may be exhaustive in typing judgment of match expression. To determine if the entailment is true or false, we need to get rid of the question mark in the constraint. If we are checking exhaustiveness, we replace the question mark with truth, just as we replace a pattern hole with a variable pattern. If we are checking redundancy of a branch, we replace the question mark in that branch with truth, and replace the question mark in its preceding branches with falsity. As we want to fill pattern holes in preceding branches with a pattern that doesn't shadow the pattern in the current branch. As a result, the unknown checking problem can be reduced to the existing solvable problem. In conclusion, we have already formalized a type system and implement the concept in a toy programming language. Now, we are still working on the correctness of the adapted checking algorithm. Next step, we'll also integrate the work into Hazel. Thanks for listening.
Thank you, Yongwei. Okay, I see a question in the text chat. Oh, you got the answer in one of the slides, so maybe it's solved. Then
where is the text chat?
Oh, text chat is in the on Clouder.
Clouder? Okay.
So,
SRC finalist presentation. There is a text channel for this.
okay, I was in a student research competition. Okay, but there's the RC finalist.
Oh yeah.
As a SRC finalist.
Okay.
Right. I did have a question actually.
Mm-hmm.
So I was wondering about the specific examples. So let's say you have a unit type, so which has only one possible constructor.
Oh, that's
then
Mhm.
And then in the first pattern, you have a hole, which for this match. And the second match has the single constructor of this type. Then, well, there's two possibilities for the hole. Either it's a variable or it's also the unit constructor. But in either case, this would be, the second case would be redundant. Is this something you can detect as well?
Yeah, that's actually something we have been considering for the like maybe the past months. Like say because so in our current in say for the implementation now, we didn't consider the unit type because of what you just mentioned.
Okay.
Because like unit type, but again, like I think unit type can be the problem of the unit type can be solved by say if we see say if we considering if the third branch here is redundant or not, and actually the expected type at the whole should be a unit, then we can just simply say, okay, no, like we can't find other pattern other than the unit pattern right here. So we can just fill it, which is like kind of a heuristic. But speaking of the proof, because we want to make the proof at least readable and not too long and too complicated to deal with, we didn't include the unit in the calculus. Yeah.
Okay, thanks.
Good for the question.
Okay. Any other questions?
It seems to me that Jasper's question applies just as well if you match on a bool and the first branch is true and the second one is a whole. It's the same story, right? Like either you will put a variable or you put false, and in both cases it's going to be covering and you have nothing left. Yeah?
Well, you could have another one that has true. So either it's redundant or it's...
Oh, right.
Okay.
Sorry. Should have left.
Are you saying anything?
So I have a question. So you mentioned that you are going to prove the correctness of checking, right? So could you please spell out the exact theorem that you want to prove?
Okay. Yeah. So that will come to the unknown. Like we want to get rid of the unknowns, like the question mark here, because if there is such a thing in the entitlement, we can determine it. So we want to prove the equivalence between these two entitlement, and we use the use the entitlement at the bottom to determine the exhaustiveness in this case. So we want to. So this is the thing I'm working on right now. And the same for the redundancy, such like this is also another equivalence I want to prove. Yeah, and also I think the other theorem that important is just those like, preservation and the progress, because that's why we want pattern match, or like, that's why we want exhaustive, right? We want to say like if we can determine this exhaustive or maybe exhaustive, then like no runtime error should be occur. Like yeah, for these things we have already proved based on the definition given here. Like we have already proved that. Yeah.
Okay, thanks.
Yeah.
All right. let's thank Yongwei again.